Hi, I'm Jack Baker. With this video, I'd like to talk a little bit about seismic source models, give you a very brief introduction. This content is taken from chapters 2 and 3 of the book mentioned at the bottom of the slide there, and we're going to cover just a few topics very briefly. So the motivation for this work is that when we do our PSHA calculation, we're going to need some input models for the sizes and locations of possible future earthquakes, and where they are, how often they occur, how big the earthquakes could be. And so in this video, I want to just give you a general sense of like how those models are characterized, so what information do we need to actually describe. Talk even more briefly, a couple of comments about how they're calibrated. We're going to skip a lot of details. We're not going to talk about the mechanics of how earthquakes will occur. The calibration is an involved process, but I'll just give you a general sense of kind of what's needed to help you appreciate what would be required for the calibration. Again, more details are in the book. So first, let's just talk about earthquakes occurrences. And maybe to motivate, let's look at this figure over here on the right. So this is a map of the world, and the circles here are showing the locations of major earthquakes historically. And then these solid black lines are showing the boundaries of tectonic plates. And so a couple things we can observe from this figure that helps motivate our work is that the occurrence of earthquakes varies widely in space over the globe. So there are some places, like on this west coast of North America that we can see in the top figure, where we have a lot of earthquake activity, and then there are other places, like in the middle of the Pacific Ocean, where there's much less activity. So the spatial variation in earthquake occurrences is important for us to consider when we think about seismic hazard at some particular location. The other thing we can notice is that a lot of these earthquakes are occurring on the boundaries of tectonic plates, where two plates are moving past each other. So that's the source of the majority of earthquakes is through shear failures associated with those plate margins, but not all of them. Right? So again, looking at the top figure, we can see these earthquakes occurring in Central and Eastern North America, not on a plate boundary. So it doesn't mean that there are no earthquakes away from the plate margins, just that there's fewer, generally speaking. Okay. And then depending on the sense of direction of motion of these plates against each other, as illustrated in this bottom left figure, there's a variety of mechanisms of earthquake occurrence that can happen, and that mechanism can be important for ground motion prediction, as we'll talk about briefly in a later video. Okay, so that's a few basic thoughts about locations of earthquakes. We also need to understand the size of earthquakes. So what we do to characterize the size of an earthquake is to measure the energy it releases. So more energetic earthquakes are bigger and potentially produce stronger ground shaking. Couple things to think about. So the first thing we're going to do is the standard measure of the size of an earthquake is seismic moment, this m naught in the first equation. And we compute seismic moment. It's the product of three terms. So we have this mu. So that is the shear modulus of the rock that is failing, or that is slipping in the earthquake. And a typical value for that in the Earth's crust is 3.3 times 10 to the 10th newtons per square meter. So that's a measure of kind of force per unit area when we have this failure of the rock. Then we have A, which is the area of the rupture. And then we have this U bar, which is the average displacement. Okay. So if we have kind of one side of a fault slipping against the other, we're going to measure the area over which that slip occurred, A. We're going to measure the amount of slip that occurred, the U bar, and then again we can take an average over that area that we've defined, which is the same thing as integrating the slip over the area. And then we're going to multiply by this shear modulus. Okay, and so if we have newtons per meter squared times area times displacement, we end up with units of force times displacement, or force times distance. Okay, and so that's units of work that's done by the rupture. Okay, so that's our basic measure of the size of the rupture. And then we more commonly use it in seismic hazard calculations. We convert this seismic moment to a moment magnitude. So So that's given by the second equation here, so m here being moment magnitude. So 2/3 times the base 10 log of the seismic moment minus 6.03. So this puts us in a moment magnitude scale where kind of magnitudes from 5 to 9 are the ones of interest for our engineering analysis. So these constants and this log 10 transformation, I'll make a note here. So those were selected to match the older surface wave magnitude scale. And that's over a kind of moderate event size. So you've probably almost certainly heard about the Richter scale for earthquake magnitudes. So that's another name for the surface wave magnitude scale. And this is a scale of earthquake magnitude that measures the kind of amplitude of shaking at a reference distance from the earthquake. And so kind of larger amplitudes indicate larger magnitudes. That's a problematic scale in that it doesn't do as good of a job measuring very large earthquakes. So what was done is to take this moment magnitude scale, which replicates that surface wave magnitude scale over a range of moderate events, but it works well up to very large events as well. And so the constants here were chosen just so we replicate the older scale, but it works more broadly. Okay. So I've mentioned surface wave magnitude scale, which is kind of the older technique. Moment magnitude is our kind of de facto standard for seismic hazard calculations. I'll just make a quick mention. There are other scales of earthquake magnitude, but moment magnitude is the preferred and the standard metric in seismic hazard studies. Okay, so we've got a metric of earthquake size. And now we want to come to our source modeling. So what we do is we define a set of seismic sources, and we, when we're doing hazard analysis at a particular site, we can think about this map over here on the right. So the site is sitting in the middle, and this is a map view. This isn't a picture of a globe. What we do is we take our site and we take some kind of radius of interest, and we circle out that far. And so our shading here in the figure kind of indicates all the locations within that radius of interest. And that radius is defined based on our goals of our analysis and how far away of an earthquake we think could be relevant for our assessment. So at some large distance, the earthquakes just aren't important for us because they're not capable of producing shaking amplitudes of interest to us. So we'll set that, and then we'll look within that radius of interest and say what sources of earthquakes could there be here that we need to think about in our hazard assessment. And those sources could be faults. So you can see in the bottom of the figure here, we've got this fault source drawn, and then ruptures could occur on part of that fault. We don't necessarily have a rupture that extends for the entire fault. We could also have an area source, so that's shown in the upper left of the mapped area. And so this is the strategy we use to define a source if we don't have a specific fault that's physically identified. We say, in this area, earthquakes can occur. All right, so we generally work with these kind of linear, planar fault sources or kind of areas or volumes for area sources. All right, and then for each of those sources, we need to now characterize the types of earthquakes that could occur on that source. All right, and so what we need specifically is what we call a magnitude frequency distribution, which tells us how often earthquakes of varying magnitudes happen. So for a given magnitude, what's the frequency of earthquakes we could expect to see there. Okay, and so I'll give you an idea of this through a Gutenberg-Richter model. This isn't the only way to handle it, but let's talk it over. So this model is based on the observation from Gutenberg-Richter a number of decades ago, that if we look as plotted here on the right, we've got a plot of the magnitudes of earthquakes versus the rate of exceedance, how often we see exceedances of that given magnitude. And there's two sets of data here. Let's just look at the orange circles. Doesn't matter much for our discussion, but this is a set of observations near Yerba Buena Island in California, kind of a location close to San Francisco, just as an example. And if we plot the magnitude, and this is moment magnitude here, versus the rate of exceedance that we see from a catalog of observations, and we plot this y-axis, rate of exceedance in log scale, so we see that these are kind of logarithmically scaling values here, we often see this linear trend in the frequency of earthquakes. Right? So Gutenberg and Richter noted this model that the base 10 log of n, which is the number of earthquakes, and that's related to the rate of earthquakes just divided by a constant for our observation window. So kind of equivalent to the y-axis on the plot over on the right within a constant. So that number of earthquakes in log 10 scale it can be described by a minus bm, where a is our intercept, indicates kind of the overall activity rate, and then b indicates this is the slope term from the plot over on the right, and so it indicates the relative frequency of large magnitude events versus small magnitude events. So as I go up in magnitude, how fast does the number of events drop, right? So the b is that slope. Okay, and Gutenberg and Richter noticed that if we take an area and we do this type of analysis, that we often see b values close to 1. So we see in the figure on the right, we fit a value very close to 1. So oftentimes that number is relatively close to 1. Okay, and so that influences some of our modeling. Okay, so that's the kind of the Gutenberg-Richter relationship. We can turn that into what we call the bounded Gutenberg-Richter distribution for earthquake magnitudes for our source model. So let's talk through this equation on the left. So we've got lambda, which is indicating a rate. So we want, and the rate of the thing in the argument. So we've got the rate of the magnitude exceeding some value small m. That's going to be equal to the rate of magnitudes bigger than some m min, where m min is the minimum magnitude of interest. So this isn't the minimum magnitude that can be produced by the source. It's just the minimum one that we're interested in for our hazard analysis calculations. And the thinking here is that these sources produce lots and lots of small magnitude earthquakes, but those are not relevant for our hazard analysis. And so we pick a threshold at which the magnitude could potentially produce shaking levels of interest, and that's where we'll start our analysis from, just for numerical convenience. So oftentimes this m min is 3 or 4 or 5, depending on the situation. Okay, so we want to know how often do we see minimum magnitude earthquakes or larger? That's the first term in the product. And then the second term in this product is the probability that the magnitude is bigger than some value given an earthquake. So the first term in this right-hand side of the equation is how often do we see earthquakes? And then the second term is, given an earthquake, what's the probability that it exceeds some m value of interest? Okay. And this f subscript m of m, this is a cumulative distribution function, and it describes down in the bottom equation here. So this is telling us the probability that this random variable m is less than or equal to small m, the argument of the CDF. Okay. And it's given by this equation here down on the right. So this is actually a converted version of the Gutenberg-Richter distribution, but just converted to a probability distribution. And so we've got these exponentials in here. Because we're working with exponentials rather than 10 to the power of something, we've got a little conversion, and we've got this beta in here. But beta is a constant, and it's equal to the natural log of 10 times the Gutenberg-Richter b value. So the log and the 10 just deal with our switching from base 10 to base e logs and exponentials. And so this is about equal to 2.3 if b is about equal to 1. Okay. So we've got the beta, which is a constant. We'd have to define source for a particular source, but it's approximately equal to 2.3. M is the number we're specifying to evaluate this function. M min, again, is that smallest magnitude of interest, and then M max is the largest magnitude that the source can produce. Right? So M max here is the largest M that the source can produce. Okay, so we talked about seismic moment was proportional to the area of the rupture, and then this moment magnitude is related to seismic moment. So we're constrained by kind of sizes of ruptures that a source can host in terms of how large of a magnitude we could see. So there is some upper limit to these sources. Okay, so we put this all together and we get this bounded Gutenberg-Richter distribution. So it's bounded on the bottom side by the magnitude smallest magnitude we're interested in. It's bounded on the upper side by some upper value that we specify. And the figure on the right here shows what that distribution looks like. This is for a b value of 1 or a beta of 2.3, and for 3 different values of the m max. So you can see how the function, these rates of exceedance taper off at the m max value, so we don't kind of head off to infinite magnitudes. Okay, so that's an example of a magnitude frequency distribution. This is not the only one that you have to use. There are so-called characteristic models that put kind of an emphasis on a large characteristic earthquake that maybe occurs frequently on the source relative to what the Gutenberg-Richter model would say. There are mixed models that include characteristic and Gutenberg-Richter distributions, and lots of different ways to do it. So I'm not specifying this to say this is the right way or the only way to do it, but only to illustrate how we characterize one of these magnitude frequency distributions. Regardless of how we set up the equation, on the left-hand side, we still need this result. We need the rate of magnitudes larger than some value. But on the right-hand side here, we could specify something different for a different type of distribution. Okay, so that's what these magnitude frequency distributions look like. Let's talk briefly about how we calibrate those things or constrain them. So there's 3 different general types of information that we can utilize. First, we're going to use the observed earthquake rates. That's kind of the data that we looked at for the Gutenberg-Richter model. We can observe all the earthquakes occurring on a particular source and try to characterize those. Here's a map or a figure on the left. This is a map of observed earthquakes. We can use their locations to try to define sources, fault sources and area sources. And then we can use the magnitudes of these events to get at this magnitude frequency distribution. We can also use the general occurrence rate of these earthquakes to get at the rate of minimum magnitude or larger earthquakes. Okay? So this works great for smaller magnitude events because those are the events we observe more frequently, and we can calibrate that aspect of the model. We don't observe the very large events very frequently, and so to get at the large magnitude events, we do a few things. We can certainly extrapolate out Gutenberg-Richter models, but in terms of direct evidence, we'll go to the right side of the figure. If we can, we'll use what we call paleoseismic evidence. So this is detecting evidence that's been left on the Earth of past earthquakes, and if we can find the evidence of that past earthquakes in geological features, we can utilize that to try to figure out when those past earthquakes happened and how often they happen. So here, let's clean this off first, and then we can talk about it. So this is a picture on the right of what's called an offset stream. This is taken from the U.S. Geological Survey photo. So what's going on here is in the distance, there's a stream bed that's kind of flowing down, and then once we get to this point here, there's this offset where the stream used to flow kind of this direction, but because of an earthquake rupture that occurred right along here, that stream bed has been offset to the left, and now the water flows up that offset and then down at a location to the left. All right, and so we can see evidence here that there was a displacement in the surface of the Earth. And if we go into that stream bed and we find some material in an old stream bed that's not flowing anymore, and we date how old that material is, we can do some analysis to figure out how long ago that offset occurred. And if we can do this a few times, we can find multiple historical or prehistorical earthquakes and try to figure out the rate of occurrence of those events. So this is an interesting line of inquiry that can give us constraints on these large magnitude events. And, this doesn't constrain small magnitude events because the smaller magnitude events generally don't leave any sort of geological evidence, and so we don't have any way to detect those types of events. The big events that leave features on the surface can oftentimes be studied in this way. Okay, there's a third line of constraints on these magnitude frequency distributions, which is the rate of strain accumulation in the crust. So this is what we can detect from geodetic observations. You can think about high-resolution GPS, and if we put GPS instruments on two sides of tectonic plates that are moving relative to each other, we can measure how fast the strain is accumulating in the crust, and then we can, if we specify how much of that strain accumulation is going to be released in earthquake events versus other types of slipping events, we can say, well, that strain that's going into the system has to be released in the form of earthquakes, And if we add up all the different earthquakes of different sizes and a magnitude frequency distribution, we can do a equating of those strain rates and get an overall rate of earthquake activity. And so we can do that even in the absence of observing the earthquakes themselves. And so that's another strategy. And so ideally, we'd like to put all this evidence together and come up with a coherent picture of these magnitude frequency distributions. This is not a trivial activity, but this is the general process that we go through to try to build those magnitude frequency distributions. Okay, so that specifies the sizes of the earthquakes and kind of how often we see or we expect to see earthquakes of varying sizes in the future. Once we've specified the earthquake sizes, we want to do some geometric calculations to think about the distances of those earthquakes. And so here what we do is we put those hypothetical earthquakes of varying magnitudes on our sources, and we can put the locations in we can vary the locations of those earthquakes within what's physically possible, and then we can compute the rupture distances. So here is a figure showing the layout of this situation. So we've got kind of in this horizontal blue line, we've got a fault, and then the three images here labeled ABC are just three different pictures of that fault. Then we've got a rupture here shown as a partial plot across this fault. So an earthquake of a given magnitude, we related the magnitude to a rupture area, remember, so that can also be related to a rupture length and then a depth. So we've got a rupture here that happens over part of the fault, and then we're going to be interested in the distance from that rupture to our site, and we're usually measuring our primary metric is the closest distance from some point on that rupture to the site. And so we're going to measure that distance and say, for a rupture in this location, here's our distance. And then what we'll do is we're going to vary the rupture location within our plausible locations. So we've got, in figure B, we've got a rupture that's all the way to the left, and we would have a corresponding distance for that case that's larger. In the panel C down at the bottom, we've got a rupture that comes by the closest point on the fault to the site, and so our rupture distance would be this kind of perpendicular distance here. Okay? So we could vary that rupture back and forth across the fault and find all the different distances and make a probability distribution. And in terms of the locations of those ruptures, one simple model is to say, well, each location is equally likely. There are also some evidence from looking at faults and ruptures that maybe the middle of the fault is a little more likely to host earthquakes, ruptures than the edges, and the edges are a little less likely. So you could make some locations more likely than others. But nonetheless, you're going to assign those all and get corresponding distances that have corresponding probabilities. These distance distributions are going to be magnitude dependent. So these are a set of plots for a particular rupture dimension. But if the rupture gets larger, then the distance metric would be different. So to take the extreme, if we had a rupture of the entire fault, right, we could kind of, I'll say, just to superimpose it on one of these pictures. If we've got this entire fault rupture, so this would be a large magnitude, large rupture area, and because it's an entire fault rupture, the distance is always going to be this RY distance, the closest distance from the fault to the site. And so for the large magnitude ruptures, we'll tend to have closer distances because some portion of the rupture will get close to the site. For the smaller magnitude earthquakes, we could have a more distant distance. Okay, so if we take and we combine together that Gutenberg-Richter magnitude frequency distribution, and we take this geometry for rupture distances, we can get a joint distribution for magnitudes and distances. So just to think through what this would look like, here's an example figure. So we've got magnitude on the left axis, distance over on the right axis, and then the height of these bars indicating the probability of that combination of magnitude and distance given that we had a rupture in the fault. So what we see in terms of the kind of left to right direction of the axis is that we have this kind of exponential fall off in probabilities, and that's the Gutenberg-Richter aspect of the model, where the large magnitude events are much less probable than the small magnitude events. And then in terms of our distance axis, we see this variation that the large magnitude events tend to have very close distances, right? So as I get to say a magnitude 7.5 or greater earthquake magnitude, I'm guaranteed to have a small distance here because of that full fault rupture geometry that we were talking about. As I get to smaller magnitude events, say a 5.5, I can trace along the 5.5 axis and I see that I've got this range of distances that's possible. So the close distances into 10 kilometers or so in this case, out to very large distances are all possible because I could have a smaller rupture very distant. So we end up with these joint distributions, and then for any combination of magnitude and distance, this distribution will specify how likely that rupture is. We'll then take those likelihoods with our ground motion predictions for each rupture in the later hazard calculations to characterize the hazard that we're looking for. Okay, so that gives you a general sense of what we need to specify to get through these source models. So a few conclusions to wrap this up. So we need to think first about seismic sources. And so a seismic source could be a line or an area, or a fault or an area. And those are specifying the locations where future earthquakes may occur. Right? And then for each of those sources, we're going to have a characterization of the earthquakes it could produce. Right? So we've got a magnitude frequency distribution, and that's going to specify the sizes of future ruptures in terms of their magnitudes and how likely each one of those is. And then once we've got a source and we've specified its magnitude, we can assign that rupture within the source and then use geometry to characterize the distance from the rupture to the site. And then if we randomly assign that rupture within the source, we'll have a probability distribution on the distances. Okay? And then stepping back from all that characterization, we think back to our original goal. What we want with these models is to extrapolate beyond our direct observational data. Right? So we have some types of observational data about where earthquakes are occurring and their distribution of magnitudes. We don't have the direct observations typically of lots of large magnitude, close distance ruptures that are the ones we're worried about for our hazard analysis, loosely speaking. But by going through this kind of systematic characterization of sources and then thinking about typical distributions of magnitudes on a source and then using geometry, we can make informed inferences about those possible rare events that could be producing very strong ground shaking. All right. And once we've got all this characterized, that is the source model characterization that's going to then serve as an input to our seismic hazard analysis calculation and get us to our ultimate goal of getting to ground motion hazard curves. Okay, so that's what we have for seismic source models.